In this video, we're going to look at something called limits at infinity. These are limits that, guess what, look like limits, and they're, instead of x approaching a number, x will approach positive or negative infinity. And this will be the limit of f of x as x approaches positive or negative infinity. These limits at infinity are also have applications with something called end behavior. And in this video, we'll also look at how we can use limits at infinity to find horizontal asymptotes. And we've already done a little bit of this before. You might recall something called Bobo-Botten eats DC. If you don't remember that, I will explain it later in the video as well. Eats DC. Let's say I have this limit. It's the limit of 3x squared over x squared plus 1 as x approaches infinity. Now, infinity is not a number, so we can't just go on and plug in infinity. Like you can't do 3 infinity squared over infinity squared plus 1 equals infinity over infinity. That doesn't make sense. Okay, we can't do that because infinity is not a number. So we have to find a different way of doing this. One way is to think about infinity and instead sort of do like the chart process. So we pick a very large number. So we're going to do the limit as x approaches big, because big is a big number, of 3x squared over x squared plus 1. And when we do this, we're going to get 3 big squared over big squared plus 1. And what's going to happen is the 1 will essentially become irrelevant because big squared is a huge number and adding 1 to it isn't going to make it that much bigger. So in a sense, we can essentially ignore the plus 1. And what we'll get is, and what we'll end up with is 3 big squared over big squared, but big and big are the same number, and so big squared will cancel out and we'll get 3. And so that's one way to think about this limit. Here's another way, and this is a little bit more algebraic. What I'm going to do is multiply the top and bottom by 1 over the largest exponent. So the largest exponent here is x squared. So I'm going to multiply the top and bottom by 1 over x squared. When I do this, I will get the limit as x approaches infinity of 3x squared over x squared, which is just 3, divided by x squared over x squared times 1 over x squared is 1, and then plus 1 over x squared. And now what I can do is I'll take the limit as x approaches infinity, and here I have 1 over x squared, and essentially 1 over infinity will go to 0. This is the limit of 1 over infinity. This goes to 0, and so I get 3 over 1, which is 3. Ta-da! This second algebraic trick also works for more complicated things. So if I have 4x cubed, blah, 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 what I will do is x cubed is the largest exponent, so I'm going to multiply top and bottom by 1 over x cubed, 1 over x cubed. And the reason I can do this is because this fraction is just 1. It's just in a very strange form. And then what I will get is the limit as x approaches infinity of 4 minus 3 over x plus 7 over x cubed divided by negative 2 plus 5 over x squared. And then what will happen is, as x goes to infinity, this will go to 0, this will go to 0, this will go to 0. I'll be left with 4 over negative 2, which is negative 2. And so these are the limits at infinity. This is how I do them. You might have noticed a shortcut here. So I'm going to present 3 very similar problems, and we can figure out what the pattern is. Here are 3 different limit problems. Notice, first of all, that these are all limits at infinity, so we're okay there. And this is the trick that we're going to use. All I'm going to do is just compare the leading exponent of each term, the top and the bottom. So in the first one, notice that the bottom exponent is bigger. So essentially, when x gets really large, the negative 8 won't matter very much, and so I can ignore it. And what I'll end up with is the habit, or not the habit, but I'll get essentially 2x squared over 3x cubed. And then some x's will cancel, and I'll be left with 2 over 3x. And then as x goes to infinity, this whole thing will go to 0. And this will happen whenever the exponent is bigger on the bottom. So I can come up with a mnemonic that says bigger on bottom, the limit will be 0. In the second example, we have a sort of flipped situation where the exponent is bigger on the top. And so if I do the same trick where I ignore everything after the leading coefficient on the top on the bottom, I'll end up with 2x cubed over 3x. And if I simplify this, I'll get 2x squared over 3. And now as x goes to infinity, the x squared is going to explode, basically, and also go to infinity. So this limit goes to either plus or minus infinity, and this is considered having no limit, or limit does not exist. And so this is, if the exponent is bigger on the top, then there is n for no limit. The last example is if the exponents are the same. In this example, the exponent on the top is 1 and on the bottom is 1. And so in this case, I have an example like my first two, where I basically ended up dividing the leading coefficients. So the 4 and the -2, I just divide them to get -2. And so in this last example, all I have to do is say, well, the exponents here are the same, and so I'm just going to divide the coefficients. You could think of it as x over x. This will give me 1. And so if the exponents are the same, then we divide coefficients, dc. So you could think about a monkey, Bobo Button eats dark chocolate if you so desire. Some practical uses of limits at infinity. The major one is finding horizontal asymptotes. So if I've given the equation of y equals x plus 1 over x plus 7, instead of plotting points, I can plot features of this graph. So here is, wait, hold on. That's right, new update, so now I have graphs. It's awesome. Anyway, if I look at this graph, first of all, I'm going to have a vertical asymptote at x equals -7, so I can count it off, 1, 2, 3, 4, 5, 6, -7, like this. And if I plug in x equals 0, that's going to give me a y-intercept of about 1/7, so there. If I plug in x equals -1, then I'll have an x-intercept. And so then I can use the horizontal asymptote, and the horizontal asymptote is the limit at infinity. Here the limit at infinity is 1, and so my horizontal asymptote is y equals 1 because that's the limit as x approaches infinity. So basically over here at positive infinity and negative infinity, the graph will approach this line asymptotically. And so when I draw the graph, it'll follow up like this, and then swoosh down the asymptote. Come on, there we go. Like that. And so that's the graph of this function. You could verify that on a calculator if you want. Sometimes just for kicks, they will throw in things like sine and cosine just to mess with you, but don't freak out, it's going to be okay. Basically, treat sine and cosine. Remember that the range of sine goes between -1 and 1. So if I have the limit as x approaches infinity of sine of x, the graph of sine of x looks like this. And as you can see, there is no limit because the y values will just continue to oscillate between -1 and 1. And so I could think about, well, if I always pick these y values, I'll get a limit of -1. But if I pick these y values, I'll get a limit of +1. These are clearly not the same, so this has no limit. Conversely, let's say we have the limit as x approaches infinity of sine of x over x. And in this case, what we can do is treat sine of x as only going between -1 and 1. And so, like, I could treat this as the limit as x approaches infinity of plus or minus 1 over x. And now, very clearly, as x approaches infinity, this entire thing will always go to 0 because x is going to get really, really big, but the sign of infinity is still going to be between plus or minus 1. And so this limit will go to 0, just like that.